Good morning, good afternoon, esteemed member of the panel, my mentor and honored guest. My name is Ritesh Mahajan. I'm here today to defend my DBA dissertation titled Exploring Artificial Intelligence Model for Rock Mass Classification and Assessment of Cost Estimation. Here is an overview of the presentation. We will start with an introduction that will include the background of the rock mass classification, followed by the literature review. Next, we will discuss the methodology used in this study and then move into the finding with exploratory data analysis and performance various machine learning model. Thereafter, discussion followed with the conclusion, limitations and future research directions, and finally highlight on the references. Rock mass classification is a method of rock mass assessment in the field of mining, geotechnical industry. Traditionally, two major classification systems has been used in the industry, Q system and RMR. This system divided the rock mass into 5 classes based on the multiple geotechnical parameters like RQD, joint reference, joint set number, joint roughness, UCS value, etc. I will discuss those parameters in detail. Generally, rock mass class 1 represent a good quality and class 1-5 represent poor quality of the rock mass. Each class have their own value, rating value ranging from say for the class RMR case class 1 value range from 91 to 100, and for class 5 rating ranges from 0 to 20. Hence, based on the types of the rock class, construction cost varies. This traditional approach, Q system and RMR method heavily rely on human expertise and field observations, which can be subjective in a complex geological condition and lead to the different result, affecting mislead project cost estimation. However, AI is a reliable approach similar to the machine learning and deep learning that can revolutionize rock mass classification by automation process, enhancing accuracy and reduce human error. My desired objective for the research work is to develop a reliable AI model for rock mass assessment and enhance accuracy while assessing the cost implication. Moving on to the problem statement, my research work study explored the potential of innovative AI-driven approach for rock mass characterization, improving accuracy, consistency, reduce overestimation, and cost effectiveness in the civil engineering projects. The study also demonstrates significant improvement in the classification performance and practical benefit through the integration of AI model. Moving on to the literature review, let's look at the existing system used for the rock mass classification. Q system. This was developed by the Barton and Lien in 1974 and uses parameters like RQD, JN, JR, JA, JW, and SRF. Rock mass rating, introduced by the Wieniawski in 1989, it considers factors such as UCS value, RQD, spacing, filling condition of discontinuities, groundwater condition, joint orientation. This system neglect the ground stress condition, SMR and GSI. These are used for the heterogeneous sedimentary rocks and were discussed by the Mirko et al. In 2019. Under this paper, a novel approach for the geomechanical classification for rock slope combined with the remote sensing and geographical information system for the slope mass classification was discussed. This system is very localized ground condition, basic quality, proposed by the Kechan et al. 2021. This method includes the intactness index, KV, UCS, RQD, and Lugen. This paper is based on the case study in China, and it's not possible to calculate the intactness index KV value in all engineering projects. Thus, it is complicated to classify the rock mass classification in a complex geological condition. Key finding. The accuracy of the rock mass assessment is crucial because any mistake can mislead the incorrect project cost and potential risk. However, AI model like logistic regression support vector machine have shown high accuracy in the various fields, including rock mass assessment for the TBM tunnel. This model could provide a reliable way to reduce the risk and improve cost estimation accuracy, as noted by the Liu et al. In 2019. There are a few research gaps found during the literature review. First one is a model accuracy. More comprehensive data set with the diverse geological settings and engineering properties are needed to improve the model accuracy. This is explained by the Lawrence et al. In 2022. Overlook AI model. Many AI models focus on theoretical implication rather than the practical applications. There is a need of the research in the scalability and adaptability of this model to different geological settings, as mentioned by the Jack Chen et al. In 2019 and Allen et al. In 2021. Our research aim is to integrate the AI machine learning model, enhance the rock mass classification accuracy and predict capabilities. This integration will help to improve the cost estimation and mitigate risk in the construction project involving rock structures. Let's go through the methodology used in our research project. We adopted a quantitative research methodology. The whole research process passes through the 4 stages. Under the stage 1, the data was collected from the government department in the PDF format and converted into numerical data like an Excel sheet. Under the stage 2, the data cleaning was done to ensure the quality of the data. We removed the null value, duplicate value, and applied ordinal encoding to categorical variables. Under the stage 3, exploratory data analysis. Under the stage 3, we identified the feature metrics and target vectors or meaningful variables that would be used for AI model. These steps help to understand the structure of the data. In the last stage, we split our data into the training and testing using 85-15% ratio. Then the baseline model was fitted into the data set to develop a dummy classifier, which is called baseline model. After obtaining the result of the dummy classifier, the performance matrices such as accuracy, precision, recall, and F1 score was analyzed. For further improvement, we performed hypermeter tuning, or we can also say scaling to optimize the performance of the machine learning model, like a logistic regression, decision tree, spot vector machine. Here is a detailed step that were involved in our research work. At the first, 64 boreholes, each approximately 40 to 45 meter deep, were collected from the GEO department. It's a government department in Hong Kong in a PDF format, and then the digitalization was done with each borehole log to form a quantitative data in Excel sheet. We selected a primary Q value system for the rock mass classification because most of the attribute under the Q value parameters can be quantified from the borehole log. We generated almost 3041 data set in Excel sheet at each 1 meter interval. Each data set was converted to the CSV file and imported into the Google Colab for the data cleaning process using the Python language. Moving on to the finding part, under the exploratory data analysis, the data was analyzed and to understand the correlation of the different variables, and which can be used for the fit of the machine learning model. Here is a scatter plot of the Q value and other variables to understand the correlation. Color coding was set based on the rock mass class. Some variables have a positive relation while some of them are negative. Some of them have no relation. You can see that here the graph shows like RQD. Once the RQD value is increased, the rock class also increased, and this exploratory data analysis suggests that the features like RQD, JN, JA, JR, JW, SRF are a significant indicator for the rock quality and can be critical to building the rock classification model for the prediction of the rock class. Now I would like to discuss about the description of those parameters which is relevant for the AI research. All those 6 parameters are RQD, JN, JA, JW stress reduction factor. Each 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 parameters have their range value from numerical range value from, say, for the RQD case it varies from 0 to 100. Similarly for the stress reduction factor is from up to 125. Now we have 3041 data set and feature matrix. This data set is randomly split into 85 and 15% ratio for training and testing purpose. For example, feature matrix split it into which is called X-train and X-test. Similarly, target vector split into Y-train and Y-test. At the first, we develop the baseline model called dummy classifier to fit the model by fitting the model on dataset. After training the model on the training features matrix target vector, we predict the model on the testing feature matrix. After predicting the value in the testing data, we evaluate the performance of the baseline models through those matrices like accuracy, precision, recall, F1 score. In terms of the accuracy, we can see the baseline model predicts correctly like about 24%. The testing with the testing data of the target value. In order to improve the performance of the baseline model, we perform the data processing through scaling the numerical values through the standard scaling API and fit the model on the X-train and Y-train dataset to train it. After we run the multiple logistic regression model, which is a classification model and also decision-based spot vector machine, we predict the row class and complete it with X and Y test value. Logistic regression model demonstrates the high accuracy, precision and recall F1 score, indicate its effectiveness of the rock mass classification. The decision tree and slope vector machine model also perform well, but slightly low matrices. Here is a visual classification report heat map for the logistic regression that shows the correct predictable performance. For example, class 1 represent 100% of the correct prediction for the precision, F1 and recall. We observe that most of the performance metrics are shown the high level of correct prediction on each rock mass class. The logistic regression model after feature the scaling the numerical will demonstrate significant improvement over dummy classifier across all the metrics. We can see during the dummy classifier it was only 24% of the accuracy level during the time after scalability of the logistic regression model shows the 98% of the accuracy level, prediction accuracy level for the rock mass classification. It provides high. So in conclusion, but we can say that it provides a highly reliable and accurate classification for rock mass quality, making far superior than the traditional rock mass classification. Here is a research questions. What are the question one? What are the opportunity exist for the improving of the rock mass classification based on the insight and literature review? Opportunities for improving the rock mass classification system include integrating AI model, process complex data, reducing human subjectivity, optimizing feature selection to enhance accuracy and adaptability. Question 2. Which geological attributes and variables have a most significant influence on the rock mass classification? Variables influencing the mostly like RQD, joint set number, joint roughness number, joint alteration number, joint water reduction and stress reduction factor. What strategies can be employed to optimize the AI model for rock mass classification? Consider affecting factors such as model complexity and computation efficiency. Strategy include feature selections using assemblage learning, adjusting model setting to balance complexity and efficiency in AI-based rock mass classification model. Question 4. How does the performance of the AI model rock mass classification compare to the traditional empirical method in terms of the accuracy and reliability? AI-based rock mass classification model leverage machine learning algorithm achieve an accuracy of 98%, significantly outperform and reduce the human subjectivity and handling complex data and adapting real-time conditions, thus enhancing overall reliability and precision. Question 5. What methodology and approaches can be employed to quantify the financial implication of the different rock mass classification outcome on the project budgets? Accurate AI classification model can link to the prediction to predict cost outcome by dynamic adjusting and estimate the best on real-time optimizing resource allocations, leading to the more accurate budgeting. Question 6. What are the practical applications of the AI-driven rock mass classification and cost estimation in the geological engineering project? This includes the optimization project operations, predicting accurate rock mass classification directly linked with the construction cost, enhancing rock safety, project safety through the real-time monitoring, reduce the budget overruns, improve the resources allocation and risk management. Moving on to the discussion part, we understood that our research that traditional method RMR, Q value, GSI are in static nature, while the AI model like logistic regression, slope vector machine can analyze large complex data and forecast accurate rock mass classification, reduce the human bias, and it's adaptable. To build a machine learning model, geological features like IQD, joint set number, joint reference number, alteration, joint water reduction factor, stress reduction factors. The research enhances the rock mass classification by integrating the advanced machine learning model, contrasting them with the traditional system through a comprehensive literature review, robust data collections, and rigorous model evaluation. It highlights the high superiority of the machine learning model like a logistic regression over baseline model, advocating for broader AI adoption in a geotechnical industry to improve the accuracy, efficiency, and adaptability. Finally, we move on to the conclusion part. This study enhanced the rock mass classification by employing the advanced machine learning models and contrasting them with the traditional approach. It demonstrates that machine learning techniques, particularly logistic regression, outperform the conventional method. The research advocates for the broader application of the AI in a geotechnical engineering to improve the accuracy, efficiency, and adaptability. Future recommendation. Future research in the rock mass classification should focus on developing the hybrid type of model, enhancing data collection and standardization, exploring the advanced machine learning algorithm, and implementing real-time monitoring along the establishment of robust validation framework and industry-wide standard to ensure the reliability and consistency in the geotechnical engineering. Here is a few references. You can see I have also put one of my references that I published a paper recently related to the innovation AI-driven approaches for enhancing rock mass characterization. At the end, thank you to everyone. If you have any questions, please feel free to ask any questions. Thank you so much.